So we're going to talk about different types of chemical bonds, and then we're going to talk about how to name different types of compounds. So covalent bonds are bonds in which the electrons are shared between atoms. Covalent bonds always occur between nonmetals. So the key features in covalent bonds are that they occur between nonmetals and that they share electrons. Some elements always occur as molecules, and I don't require you to memorize these, but you should get familiar with them and recognize when you see them that they are elements that will always occur as diatomic molecules, meaning that there will always be two of them. If you like little mnemonics or things to help you remember, you can remember those elements as Brinkelhoff. So the elements that always occur as diatomic molecules are Br2, I2, N2, CO2, H2, O2, and F2. Ionic bonds are bonds in which the electrons are transferred from one element to another. So ionic bonds occur between a metal and a nonmetal. The metal is the one that gives up its electrons. It becomes positively charged. We call that one a cation. A nonmetal is the one that takes the electrons. The nonmetal becomes negatively charged, and we call that an anion. So if you want to use a little bit of word association to help you remember this, the negatively charged nonmetal is the anion. That's the one that has the extra N in it. So, when we're going to name a compound, the first thing we need to determine is whether it is ionic or covalent. If it's ionic, meaning it has a metal and a nonmetal, there are going to be different rules for naming the compound than there are for covalent compounds, which are all nonmetals. So we first determine whether something is ionic or covalent, and then we use the rules for that particular type of compound. So let's start with covalent compounds. So you will also see covalent compounds referred to as molecular compounds. So if you see the term molecular, it just means the same thing as covalent. For covalent compounds, we use prefixes to tell us how many of each type of element we have. And then we change the ending of the second element to "ide." So you will need to memorize these prefixes. So 1 is mono, 2 is di, 3 is tri, which these are probably fairly intuitive. These are prefixes that we use quite frequently for 1, 2, and 3. And we keep going for tetra, 5 is penta, and so forth, all the way down to 10 is deca. So for example, SO3, there's only one sulfur and there are 3 oxygens, so we would call this sulfur. There's 3 oxygens, so we put the prefix tri here, and we change the ending to "ide", so we would call this sulfur trioxide. P2O5, there are 2 phosphorus, so we call this diphosphorus. 5, the prefix is penta, so we call this pentoxide. Now there are a couple more things to remember about naming covalent compounds. When we only have one of the first element, we don't use the prefix mono. Now we do use it for the second element. So for example, when we named SO3, you might have noticed that we didn't put mono on the first element. We would not call this monosulfur trioxide. We would just call it sulfur trioxide. Now, if we have something like CO, we would not call this monocarbon. but we wouldn't call the second element, so we wouldn't call it monocarbon monoxide, but we call it carbon monoxide. We do keep mono for the second element, just not for the first. Also, when we have prefixes that end in O or A, we drop that O or A if we're putting them in front of an element that starts with a vowel. So, for example, if we have P4O10, we would not call this decoxide, we would just call it decoxide. We do that just to make the pronunciation a little bit simpler. There's a few instances where when you have a prefix that ends with a vowel and then an element that starts with a vowel, the pronunciation gets a little bit awkward. So to avoid those instances, we just drop the vowel. So we would call this one tetraphosphorus decoxide. Let's look at a few examples here. We have PCl3, so P is phosphorus, and we don't use mono for the first element, so we would just call this phosphorus. There are 3 chlorines, so we call this tri, and we change the ending of the element to I, so this would be phosphorus trichloride. The second one here, BrF3, Br is bromine, F is fluorine, and there are 3 of them, so we would call this tri, and then we change the ending to I, so this would be trifluoride. So note here on the spelling, if you're putting this into an online homework system, some of them can be a little bit picky about the spelling, and it's just because of the way the computer program is. It just can't recognize if it's not spelled the way it's been programmed for the answer. It just doesn't recognize your answer as what it's looking for. Some of them are a little bit better, and they will recognize that that small difference is just a difference in spelling, but some of them are not very good with it. So if you're having trouble with one that has fluorine in it, double check the spelling, because fluorine or fluoride is not spelled quite the way you would think it is. Some people will put just OR, or they will put OUR. It's actually UOR. So if you're doing an online homework system and it's giving you a little bit of trouble with one that has a fluorine in it, just double check how you're spelling it, because it may just not recognize the spelling and not realize that you're trying to type in fluoride. Let's look at another example here. N2O. So there's 2 nitrogens, so we do need a prefix when there's more than one of the first element. So we would call this dinitrogen. And there's only 1 oxygen. We do use mono for the second element, so we would call this dinitrogen monoxide. Let's try the second set here. We're going to go in reverse. So we have carbon dioxide. We know that we don't put mono on the first element, but the only time we drop the prefix on the first element is when it's mono. So we know if there's no prefix, that means there's only 1. Dioxide, di means there's 2, so that would be CO2. Again, carbon means there's only 1. Monoxide means there's only 1 oxygen, so we would just have CO. Dinitrogen tetroxide, di means there's 2. Tetra means there's 4, so we have N2O4. Nitrogen monoxide, there's no prefix, so we know there's only 1 nitrogen. Mono means there's only 1 oxygen, so that would be NO. Now, when we name and write formulas for ionic compounds, we first need to know what the charges on those elements are. And we know what the charges are by what group they're in. Elements in group 1 or 1A always have a 1 positive charge. Elements in group 2 or 2A always have a positive 2 charge. And elements in group 3A or 13 always have a positive 3 charge. If we go over to the halogens, those always have a negative 1 charge. The elements in group 16 or 6A always have a negative 2 charge. 5A or 15 always has a negative 3 charge. And then if we're in group 14 or 4A, these can take on either a positive or a negative 4, depending on what they're bound to. So you will need to have these charges memorized, because you're going to use them quite frequently. When we name ionic compounds, we always start with the cation, which is our positively charged metal, and then we put the anion after it. So the name is always the metal cation plus the nonmetal anion, and we change the ending of the nonmetal anion to "-ide". So for example, if we were going to make a compound from sodium and fluorine, we would call that sodium fluoride. Now, unless it's noted that the compound has a charge, the subscripts have to be written so that we balance the positive and negative charges. We have to have a neutral compound, which means the charges have to add up to 0. And never, ever, ever use a prefix on an ionic compound. Those are only for covalent compounds. We don't need prefixes on ionic compounds because we can figure out how many of each element should be in the compound based on the charges. So as I said, when we're writing ionic compounds, unless it's noted that there's a charge, we always have to have the compound be neutral. So for example, if we have magnesium chloride, if we look at magnesium, it's in group 2 or 2A, which means it has a 2 positive charge. Chlorine is one of our halogens, which means it has a negative charge. Because chlorine only has a 1 negative, and magnesium has a 2 positive, we need 2 chlorines for every magnesium, so that the charge adds up to 0. Give you a few more examples here. If we take sodium chloride, sodium is in group 1 or 1A, so it has a 1 positive charge. Chlorine has a 1 negative charge, so we balance that. 1 positive and 1 negative adds up to 0, so we only need 1 of each of those. If we take magnesium oxide, magnesium has a 2 positive charge. Oxygen is in group 6A, so it has a 2 negative charge. 2 positive plus 2 negative adds up to 0, so we only need 1 of each of those. Now, if we look at something like aluminum sulfide, this is where we can start to run into a little bit of a challenge. Because aluminum has a 3 positive charge on it, but sulfur has a 2 negative. So we have to find some way to make these charges to have a number of each of these elements so that the charges add up to 0. So there's a couple ways you can do this. One way you can do it, and the way that I typically do it, is I look for the smallest number that both of these charges would divide into. So the smallest number I can think of that 3 and 2 divide into is 6. So I'm going to try to get 6 positive and 6 negative. Well, 3 goes into 6 twice, which means that I'm going to need 2 aluminums, because if I have 2 aluminums that each have a 3 positive charge on them, that adds up to 6 positive. And then if I'm trying to get 6 negative, 2 divides into 6 3 times. So if I have 3 sulfurs that each have a 2 negative charge on them, I end up with 6 negative. So that means I would need 2 aluminums and 3 sulfurs to make this compound neutral. Some people also try to do a crisscross method where they'll take the charge and make that the subscript of the opposite one. Oops. So let me get rid of this line here. So they would make the 2 the subscript on the aluminum and a 3 the subscript on the sulfur. Now that happens to work out if your charges are 3 positive and 2 negative. It doesn't always necessarily work out for every single combination. So typically I will go with doing this the method of finding the smallest number that both of them will divide into. Now, a couple more things that we have to deal with ionic compounds. One is polyatomic ions. So I will give you a table in class of polyatomic ions that you will need to memorize. You will need to know the formula and the charge for these. So polyatomic ions are covalently bonded charged groups of atoms. So they function as a group, they're covalently bonded together, and they function in the same way that an anion would. So CO3 2 negative, CO3, functions in the same way as a sulfur anion would. It's just that it's a group of atoms rather than just one anion by itself. So all of these have names. You will need to know the names, the formulas, and you need to memorize your charges on them. Because when we get later on into writing different types of reactions, you're going to find it very difficult to write some of those reactions and balance everything if you don't know the charges on your ions. And even now, it's going to be tough writing some of the formulas if you don't know the charges. So make sure that you memorize your charges, not just the names and formulas. So let's take a few examples here. When we name ionic compounds that have polyatomic ions, we keep the name of the ion as it is. So for example, if we have BaNO3 now, what the parentheses means with this 2 outside is that we have 2 of these nitrate ions. Whenever you need more than one polyatomic ion in the formula, we put it in parentheses and then we put a subscript on the outside to indicate how many we have. Now, you only need parentheses if you have more than one of the ions. So, for example, if you look at CaSO4 here, this only has one of the sulfate ions, so we would not put parentheses around it. So let's try to name this. BaNO3. Ba is barium. And if we look at the table over here, NO3 negative is nitrate. So this would be barium nitrate. If we look at CaSO4, Ca is calcium. SO4, if we look and find it in our table here, SO4 is sulfate. Now another thing to notice is when these are part of a compound, the charges are not written there. If you're writing the ion by itself, you write the charges. But if you're writing as part of a compound, it should not have a charge on it, because the charges on these compounds should add to 0. So for example, sulfate has a 2 negative charge. Calcium is in group 2 of the periodic table, which means it has a 2 positive charge on it. 2 positive plus 2 negative is 0, so we have no charge written here. So when you write the formulas for these, do not write charges on the polyatomic ions. Your formula should be written so that the overall charge is 0. So let's look at a few examples here. Sodium dichromate. So sodium is Na. and it has a 1 positive charge on it because it's in group 1. If we look at our table here, dichromate is right here. Dichromate is Cr2O72 negative. Now dichromate has a 2 negative charge on it. Sodium only has a 1 positive. So that means I'm going to need 2 sodiums to go with the 1 dichromate ion. Since I only have 1 dichromate ion here, I do not put it in parentheses. Let's try another example here. Potassium bisulfite. So potassium is K, and it's in the same group as sodium, so it has a 1 positive charge on it. Bisulfate is HSO4 negative, so potassium has a positive charge, bisulfate has a negative. 1 positive plus 1 negative would add up to 0, so we can just write this as KHSO4. Okay, the last thing we have to talk about with ionic compounds is transition metals. So transition metals are a separate category because transition metals can have more than 1 charge. So the way that we indicate that when we write its name is we use a Roman numeral to indicate the charge. Because if we don't do that, all of these transition metals can take on multiple charges. So without something there to indicate the charge, we have no way of knowing what the charge is on that particular transition metal. Now this here is just a few examples. This is not an exhaustive list of all of the possible charges. For example, manganese can have like 7 different charges, anywhere from 5 negative to 2 positive. And there are several of these that can take on 2 or 3 or 4 or up to 5 or 7 different charges. So this is just to give you some examples here. But whenever you are naming a compound that has a transition metal, you must include the Roman numeral to indicate its charge. So let's take a look at a few examples here. Now, the Roman numeral indicates charge. It does not indicate how many of the metal you have. Okay, so sometimes students will confuse that, and they'll write for 10 that there are 4 10s because there's a 4 in Roman numeral next to it. That is not the way what that is there to indicate. What that 4 tells us is there is a 4 positive charge on 10. So if we're going to write the formula for this, oxygen is in group 16 or 6A, which means it has a 2 negative charge on it. So if we want this compound to be neutral, we need 2 oxygens to go with every 10, so that we have a total of 4 positive and 4 negative. So the symbol for 10 is actually SN. We need 2 oxygens to balance that 4 positive charge, so it would be SnO2. You would not write this as SN. Okay? That would not be correct. Roman numeral is not telling you that there's 4 10s, it's telling you there's a 4 positive charge. Okay, so I stress that because that's very easy to get confused about. Let's try another example here. We have iron 3 plus, because this Roman numeral 3 tells us this is 3 positive. Sulfur is in the same group with oxygen, so it has a 2 negative charge on it. So if we're going to write a formula for this, this is going to be like the aluminum sulfide example we looked at earlier. We're going to need 2 irons to go with every 3 sulfurs to balance this compound. Now let's try going in the other direction. Now what we have to do to figure out what Roman numeral to give these transition metals is we look at the charge on the anion, and then we figure out what the charge on the metal would have to be to balance that. So in this case, oxygen is in group 16 or 6A, so it has 2 negative charge on it. That means since there's only one copper, there has to be a 2 positive charge on that copper to balance that 2 negative charge on the oxygen. So we would call this copper 2 oxide. Now let's take another example here. We know oxygen has a 2 negative charge on it, but there are 2 of them. So that means that this titanium has to have a 4 positive charge to balance those 2 oxygens. So we would call this titanium 4 oxide. Okay, so let's try a few more examples here. NaCl. Na is sodium, that's one of our main group elements. So we would call this sodium chloride. Now chromium, if you look at your periodic table, is one of our transition metals. So if we look at chlorine, chlorine is one of our halogens, that's in group 17 or 7A, which means it has a negative charge on it. But there are 3 of them, which means this chromium has to have a 3 positive charge on it. So we would call this chromium 3 oxide. Okay, so let's write a couple more chemical formulas here. So this Roman numeral 2 tells us we have a 2 positive charge on zinc. Nitrogen is in group 15 or 5A, which means it has a 3 negative charge on it. So we would need 3 zincs to go with every 2 nitrogens to make this compound neutral. This Roman numeral 1 here means that we have a 1 positive charge on copper, and there's a 2 negative charge on oxygen. So we need 2 coppers to go with every oxygen to balance that. To wrap up, we also need to talk about naming acids. So sometimes you will see a compound that has hydrogen in it, and it's a member of a class that we call acids. So when we release an acid in water, it usually releases hydrogen ions. If we mix an acid with water, then it releases those hydrogen ions, so we give it a name that designates that it's an acid. If we're naming a binary acid, which means it has hydrogen and something else, we change the word hydrogen to the prefix hydro, and then we change the ending of the second element to IC, and then we add the word acid. So let's take a look at a couple of examples here. If we have HS, if we were naming this as a gas, we would call it hydrogen fluoride. We change hydrogen to hydro, and then we change the ending of fluoride to ic, so it's hydrofluoric acid. Hydrogen chloride, we change the beginning to hydro, we change I to ic, so it's hydrochloric acid. If we have HBr, we're going to do the same thing. We're going to change the hydrogen to hydro, we're going to change bromide to bromic, and we would call it hydrobromic acid. So take a look at the last two and think about what you would name those. And I'm going to give you a few seconds to do that, and then I'll put the names up. So HI, we will call that hydriodic acid. H2S, we would call this hydrosulfuric acid. Now, when we're naming acids that have oxygen as part of the acid, so compounds that contain hydrogen, oxygen, and at least one other element, but they're bonded in a way that we have an acidic compound. A lot of times these are actually hydrogen combined with a polyatomic ion, and the polyatomic ion just happens to be one of the ones that contains oxygen. When we name oxyacids, we omit the hydrogen. We start with the root name of the anion. If the anion ends in -ate, we change the ending to -ic. If it ends in -ite, we change the ending to -us, O-U-S, and then we add acid to the name. So let's take a few examples here. HC2H3O2, if you look up this anion, that's the acetate ion. So we change this to acetic because that ends in -ate, so acetic acid. HNO3 is nitrate. We change the -ate to -ic, so that would be nitric acid. HNO2, nitrite, we change the -ite to -us, so that would be nitrous acid. HClO4, this is perchlorate, so we would change the -ate to -ic, and we have perchloric acid. H2CO3, CO3 is the carbonate ion, so this would be carbonic acid. H2SO4 is sulfate, so we call this sulfuric acid. So we don't call it sulfic acid because that just sounds a little bit odd. So this is one that we do change the pronunciation a little bit on. So we call this sulfuric, not sulfic. And similarly for SO3, we don't call this sulfurous acid, but sulfurous acid. H3PO4, we don't call this phosphoric acid, so this is kind of like the sulfuric. We would call this phosphoric. So this wraps up naming, and we'll get a lot more practice with this in class.